Lecture 17 is the first of 3 lectures on modern theory of solids. So in this lecture, we talk about the molecular orbitals, and then talk about how the bands are formed in solids, and then the band structures of metals and semiconductors. So first, students should be able to compare the bonding and anti-bonding molecular orbitals in terms of wave function, probability distribution, and energy. So start with separate atomic orbitals. When the wave functions being put together to form a molecular orbital, we can have a linear combination in terms of addition or subtraction of the wave functions to form the so-called bonding and anti-bonding orbitals. The bonding orbitals will have probability enhanced in the middle of the 2 atoms, and the anti-bonding orbital will have the probability reduced, actually suppressed to 0, right at the center of the 2 atoms. So this creates a difference in energies of these molecular orbitals. The bonding orbitals, because the electrons are sharing in the middle, it will lower the overall energy. So that's why we have this bonding orbital having the lower energy than the 2 individual atomic orbitals. And any bonding orbital will actually have the energy enhanced. So the second student learning outcome is to describe the formation of energy bands in solids. When we have a large number of atoms put together to form a solid, then the number of atoms will interact, and that means the wave functions of each of those individual atoms will start to being put together in different kind of linear combinations to form all the electronic orbitals, electronic states in a solid. And that give you a large number of different kind of combinations, and obviously the corresponding energy will vary. However, the overall energy range for all those large number of states will be on the order of several electron volts. So effectively, all those number of energy states are going to be sort of distributed continuously in the energy scale. So that forms a so-called band. And for example, if you start with a 2s electron of lithium atoms, you are going to form a band with a distribution of energy. And then since we only have 1 electron per atom, and we have a total of 2n states that are available from those molecular orbitals or electronic states in the solids. So in the case of lithium, we're going to fill only half of the states toward the lower portion of the band, and the upper portion will be completely empty. But obviously, we have other atomic orbitals, and then, for example, the 1s orbital is completely filled in the lithium atom. However, the lithium atoms, as they are put together, the interaction between the 1s orbitals will be very minimal because they are very closely bound to the shell. So overall, the interaction among the 1s orbitals on individual atoms will be relatively small. So that's why the corresponding band will be very, very narrow. However, you have these 2p and 3s, even though you don't have electrons in them, they do also still form bands, and these bands may actually overlap with the 2s band. And at ground state, obviously, electrons prefer the lower energy states. They are going to be filling the lower portion of the 2s band. The third student learning outcome is to distinguish the major differences in the characteristics of energy bands of metals and semiconductors. For metal, as we have seen in the case of lithium, we have a particular band that have a lot of electrons filling that band, but at the same time, we also have a lot of electronic states not filled with electrons. So, and then the highest energy we have with electron filling, we call that Fermi energy, and then the energy difference from the vacuum level to the Fermi energy, we call that work function. So essentially, at 0 Kelvin, all the states below the Fermi energy will be filled, and all the states above the Fermi energy will be empty. So the band structure of the metal is really characterized by having the Fermi energy somewhere in the middle of the band. And that also means that in the same band, we're going to have electrons filling, a lot of states filled with electrons, and a lot of states not filled with electrons. So this band is partially filled. In the case of semiconductor, they are held together by covalent bonds. And then so if we have these unpaired electrons forming covalent bond, we have the bonding orbital, in which case we have the electron, a pair of electrons, and then we have the anti-bonding orbital, which have no electrons. So as you go to a solid, then the bands will develop from both the bonding states and the anti-bonding states. And it happens to be that the valence band, the bands developed from the bonding state, will be completely filled with electrons at 0 Kelvin, and then the bands developed from the anti-bonding orbitals will be completely empty. And these so-called conduction band will be separated by a particular energy gap from the valence band. This energy gap typically is on the order of half an eV to maybe 3 to 4 eV. So at 0 Kelvin, for the semiconductors, the valence band will be completely filled with electrons and the conduction band will be completely empty. So this is the end of the review.